to work in the theory of simulating the gas surface interactions and dynamics. After this postdoctoral stage, he moved back to Argentina, and there he was a permanent researcher at the National Research Council in Argentina, CONICET, and currently he's an investigador principal in CONICET, and he's also a professor titular in the University of Rosario. Regarding his research interests, he and his group have been involved in trying to understand the different issues related with the gas surface interaction, the interaction of molecules and reactivity at surfaces. And what I have to remark in this respect is that his work has been pioneer in many of the theoretical methods that has been relevant in order to try to construct accurate multidimensional potential energy surfaces. And this is important because in that way, we have been able, many of us, to really simulate in a reliable way the reactivity and the scattering of molecules at surfaces. So today, Fabio, I think he's going to talk about a kind of controversy regarding the theory view of experiment performed in regarding the hydrogenation of methane in the stepped platinum surfaces. So Fabio, when you want.
Thank you very much, Maite. Good morning, everybody. Thank you very much for coming. Thank you very much, Maite, Iñaki, Ricardo, for inviting me, as usual you do. For me, it's a big, huge pleasure to come here every time I can do it. I enjoy a lot my stays here from a scientific and human point of view, so thank you very much. Okay, let's go to work a little bit. The point, can you see the pointer? Yeah. Okay. This is the title of my talk. I will talk about site-specific selectivity of stepped platinum surfaces for methane dehydrogenation at low temperatures. As already mentioned by Maite, I work in Rosario. This is our institute, is the Institute of Physics in Rosario, that belongs to both CONICET, that is the Argentinian National Research Council, and the National University of Rosario, where I also teach. I do research in this building. This is the institute, and the building in the faculty is not far from this institute, and I teach there. It's in the city of Rosario, that is 300 kilometers from Buenos Aires. This is today our group. I take a few seconds to introduce the people in our group. And I would like to mention the main areas of research we are working on in our group during the last time. One of the topics is concerning the description from a dynamical point of view of the reactivity of reactive aspects of the interaction of small molecules with metal surfaces. In particular, during the last couple of years, we are performing molecular dynamic simulations based on potential energy surfaces that are described using neural network techniques, based always in ab initio calculations. And concerning this topic, we are collaborating. We have a collaboration with the group of Maite and Iñaki, and we are working together on this kind of on some applications of these techniques with them during my stay here. This is one of the lines of research in our group. This is a second line that is led by Paula Bufager, that concerns bigger molecules on metal surfaces. self-assembled monolayers of organic molecules, organometallic molecules, and we are trying to understand also experiments coming from experiments of electrocatalysis. So always with a theoretical point of view, starting from ab initio calculations, DFT calculations. This is a second topic that might be interesting for you. If you have questions, we can discuss later. And the third topic that the third line of research in our group is led by Pablo Lustenberg. Now he's a Marie Curie Fellow in Madrid. He's working in the Catalysis Institute in Madrid, and he worked in a close collaboration with Veronica Ganduglia Pirovano there. She was born in Argentina, but she lives in Spain. She has a permanent position there, and he's now Marie Curie Fellow there. The topic of research in this case is small molecules again, like here, but with more complex substrates, in particular oxides with supported metal atoms. They are trying to understand better what happened in a condition that is closer to real catalysts that are supported metal atoms or clusters or nanoparticles supported on oxides. So these are the three topics of research on which we work in our group. But my talk will be more focused on something that could be in this line of research, small molecules on metal surfaces. Okay, why studying methane dehydrogenation? Well, the dissociation of methane is the rate limiting step of the steam methane reforming reaction that is used in industry to produce molecular hydrogen. So the dissociation, so the interaction of methane with metal surfaces has attracted a lot of attention due to to the importance of this process. But this reaction, in principle, takes place on surface of catalysts that, in fact, are nanoparticles that look something like that on a support, and these nanoparticles are not flat surfaces, but they present different facets and metal atoms with different coordinations. So the typical surface science approach to try to get closer to these kind of situations, we can say, where the molecule interact with metal atoms with different coordination, is to consider in typical surface science experiments and simulations vicinal surfaces which consist in a regular arrangement of steps and terraces. This is a way to do very well controlled experiments and on very well characterized surfaces, but with something closer to this kind of complex surfaces, at least more than the simplest case of flat surfaces. So this is our approach, and I will be talking about in this talk about these three surfaces: the 111 phase of platinum, that is the flat surface, that is considered as a reference because it is a flat, is much simpler a system to perform studies. But then the focus of the talk will be the methane, what happened when methane dissociates on this vicinal surface of platinum, that is the platinum 211 surface, and also the surface, the phase 110 of platinum that undergoes a spontaneous reconstruction at least at low temperatures, that is presenting a 1/2 periodicity, that is a kind of missing row reconstruction, and makes that this surface looks quite similar to this one. And so we will compare these two surfaces with the results for the flat surface, that is the 111. So the motivation of our work comes from some experiments that have been performed in the group of Rainer Beck in EPFL, École Polytechnique Fédérale de Lausanne, in Switzerland. And what they have been able to quantify is the probability of a molecule arriving to a row of platinum atoms in the step in comparison with the probability of dissociating methane molecules when they arrive close to a platinum atom in the facet of this vicinal surface, the 211. And they were able even to evaluate quantitatively the different probability to dissociate a molecule on different sites, so to quantify the different reactivity on the surface depending on the platinum atom they are looking at, on the step and in the terraces. This was possible thanks to reflection absorption infrared spectroscopy experiments. And let me show you what happened, what they detect when they do the first experiment in a flat surface. When they send molecules with a molecular beam, methane molecules on this flat surface, what they observe later with the RAIRS technique is a peak corresponding to a vibrational excitation of the methyl group that has been produced after methane dissociation on the surface. So they detect a peak that corresponds to the symmetric stretching mode of CH3 produced on the surface due to the dissociation of methane into H plus CH3. And this is the peak they observe when they perform the experiment with a methane molecular beam impinging on this flat platinum 111 surface. However, when they use the platinum 211 surface that consists of 3-atom wide 111 terraces, separated one with respect to the other by 100 steps. That means the geometry of this step is a square. I mean, they look like the 100 surface of platinum. But they have very narrow but still visible terraces presenting the 111 symmetry. So when they do these experiments, the surface exposes 3 kinds of atoms that are usually called the step platinum atom, the terrace platinum atom, that are the atoms that are in the middle of this small terrace, and these atoms that are called corner, that are in the corner just below the 100 step. So this surface exposes 3 types of atoms, of platinum atoms. 2 of them are quite reactive, the step one and the terrace one, as I will show you in the following results. And this one is not does not present a high reactivity, so methane molecules do not dissociate on these sites. They only can dissociate on step sites and terrace sites. Okay, so what they observe when they perform the experiments is that, in contrast with the case of the flat surface, they observe 2 peaks in the same range of frequencies. The first one, with the lower dose exposed to the surface, they observe 1 peak, that is this one, and a small peak at the lower frequency, and the high of this second peak start to increase when they increase the dose. But what is important here is that there is a peak at the higher frequency that appears first, and that can be associated with dissociation in the most reactive site, because it's there where dissociation is more favorable and takes place before, with a smaller dose. When they increase the dose of the molecules, they observe 2 peaks because they are dissociating the molecules in both sides. Let me show you these results also that are resolved in impact energy. When they use molecules with this impact energy, 56 kilojoule per mole, they observe a signal that is very small coming from this peak, and a much bigger signal that might correspond to the area below the peak, below each peak. This signal is associated to has been obtained from the second peak, the one with the higher frequency. So what we see is that at the given energy, relatively low energy, they observe a much bigger intensity of this peak, the one with higher frequency, than for the peak with the lowest frequency. And this so point to this peak to be, again, the one associated with the site with the higher reactivity. If they increase the impact energy, they can increase the signal coming from the second peak, because for molecules with higher energies, they can also dissociate on the less reactive site, that is the terrace site. So all these results point to the assignment of these two peaks in this way. The higher frequency one would correspond to a species, to a methyl species in principle, on a stepped platinum site, and the lower frequency one to a methyl group that is produced by methane dissociation on a terrace site. All these different peaks can allow to quantify the different probability of a molecule to dissociate when they land on the surface near a step site or a terrace site, because these two situations, these two absorption sites, are separated by a relatively high activation barrier for diffusion. That means that the molecule that dissociate on a terrace site will produce a methyl group in a terrace site, and the diffusion barrier to move this methyl group from the terrace site to the step site is quite high. So if they work, since they work at a relatively low temperature, below 200 K, the molecules that dissociate on terrace sites, apparently everything indicates that stay there, the product, the methyl group produced for in the dissociation, stay there. So they can be, because here they are measuring the signal of the products, and everything points to the fact that the products remain on the site where the molecule was dissociated. And that's why this allows this assignment and this allows to quantify the dissociation on two different sites. You follow what I mean? If diffusion is efficient, they can after dissociation, then they cannot they would not be able to use this to quantify the probability of dissociation. But it is not the case in principle, because there is a high barrier. This is the value of the barrier, of the energy barrier we obtain in DFT calculations for the diffusion from a methyl group from the terrace site to the step site, that hinder this diffusion. And this is something that allows these experiments to connect these experiments with the reactivity of each site. Okay, so far so good. When we superimpose the two peaks they measure with this technique on the 211 surface, we can see that the peak that is associated with methyl group in a terrace has a frequency that is very close to the frequency of the methyl group in the extended 111 surface. And the peak that is associated with a methyl group in the step site is slightly shifted to higher frequencies by 17 wave numbers. If they perform the experiment now also Oh, sorry. Here it should say 110 surface. This is this surface. This corresponds to this surface that looks like this one. If they do the experiment in this surface also, and we superimpose the three spectra, we see that the peak they observe in this case has a frequency that is very close to the highest one they observe here, because in this case it is obtained in DFT calculations and in agreement with experiments that methane only can dissociate on top of what they are called rich atoms. I mean, the atoms that look like the step one here, the one that are in a kind of step, okay, in this surface. But the molecules in this case cannot dissociate in the facets that are even narrower than in the other case. So in this case, everything indicates that there is only one dissociation site that looks like the site here that we call step site. And in agreement with this picture, the peak they observe has a frequency of the product of dissociation, has a frequency that is close, very close to the frequency they observe for the species that is in the step of this surface. On the other hand, the peak of the species that is in the face, in the terrace site of this surface, is very close to the frequency corresponding to the extended one. So far, everything is okay. First question, or first surprising result. The first surprising result is the frequency of the peak of the species that is absorbed in the step, that is a more reactive site, is higher in frequency than on the terrace. Why is this surprising? Well, because we expect that if the binding with the surface is stronger, as expected in the more reactive site, the intermolecular vibrational softening should be higher, and the frequency is expected to be smaller than in the other side that binds slightly less strongly. So we would expect the symmetric stretching frequency of CH3 on the step site to have a lower frequency that in a terrace. This is what we expect. And this is what happened with the stretching frequency of CO on this surface. On the step, the frequency is smaller than for CO in the terrace. And in addition, if we perform DFT calculations and we compute the frequency of the methyl group, the symmetric stretching frequency of the methyl group in a step site, we obtain a lower frequency than in a terrace site. So there is something that we cannot explain, the fact that the frequency of the peak they observe for the step is higher than in the terrace. This is a kind of puzzle. The second question that is open when we look at the experiments, these experiments where the results were published in 2018, was what they observed when they dosed the surface with CH3D instead of CH4. In the case of a flat surface, they observed two peaks that can be easily understood, because when we dose the surface with this molecule, you can break two kinds of bonds, CH or CD. If you break a CD bond, you generate on the surface a CH3 product. And if you break a CH bond, you produce CH2D on the surface. So when they perform the experiments on the flat surface, they observe two peaks corresponding to symmetric stretching of this species, and they correspond to CH3 and CH2D. This is the case of a flat surface. When they dose with this molecule, this kind of stepped surface, we have four possibilities in principle to break a CH bond or a CD bond, again, but we can observe the product in the terrace or in the step. So we would expect four peaks. 2 for CH3 product in the step, and 2 for CH2D product in the terrace. When they observe the spectra, the spectra they obtain 5 peaks instead of 4. And they note that this peak, in fact, corresponds to a species that is partially deuterated, and it is associated to a species in the steppe. So the question is, what is the origin of this splitting of the peak that in principle correspond to the species in the steppe? Okay? And they didn't have a question. So in some papers, I copy here the question that were open after analyzing all these experiments. And all these results were the motivation for our study. So let me show you this just because this is important to keep in mind. When we look at, CHX with X equal 1, 2, or 3, I mean CH, CH2, or CH3 on platinum surfaces, what is observed is that when we look at CH3, what is obtained in DFT calculations, and in principle is in line with experiments, is that the methyl group adsorbs on top of a platinum atom, on a top side. When we have CH2 adsorbs in a bridge site between 2 platinum atoms. And if we have CH, for methane after losing 3 hydrogen atoms, this species adsorbs in a chemisor in a 3-fold side with 3 platinum atoms. That means that always on platinum surface, what happens is that the carbon atom preserve a coordination equal to 4. Okay, this is something to keep in mind because it is important for what follows. Okay, so with the open questions that I've explained in the previous slide, we try to understand what happened, and so the first thing we try to see if including van der Waals in the DFT calculations could explain the experiment, in particular the higher frequency that was observed for methyl group in the steppe with respect to methyl group in the terrace. But we tried different functionals, including van der Waals in different ways, and nothing changed. The frequency in the steppe always was smaller than in the terrace for a methyl group on platinum 211. So then we say, okay, but in the experiments, they never have a single molecule. So we put different molecules on the surface in terrace sites, on steppe sites, to see if having 2 molecules close to each other in different sites might affect the frequencies of the species. And no, the answer was no. Always we continue obtaining a frequency on the steppe smaller than in the terrace site. And then we say, okay, but we also have hydrogen atoms on the surface. And we obtain that in most cases, the frequency on the terrace was always higher than on the steppe, according to our DFT calculations, except in a particular case where we put many hydrogen atoms near the methyl group, but the energy is very high. So it is not likely that this might explain the experiments. So nothing seemed to work. And what happened in this case is always, oh, okay, DFT is not perfect. We might have errors. And so the explanation in that moment was probably DFT is wrong. Probably DFT cannot explain these experiments. And that's it. But we were not happy with this possibility, and we try stronger to find a different explanation of this situation. And let me show you what we have obtained after many calculations, several months later, after the first publication, in which we were not able to explain the experiments. What we did was to study and compare the stability of all the possible dissociation products, or all the intermediate species of the full dehydrogenation of methane. This case is for platinum 111. What we have here, if we set at 0 the energy of CH4 in vacuum, the dissociation, the full dehydrogenation of methane on platinum 111 presents this landscape or this energy pathway for the full dehydrogenation. There is a barrier for the first dehydrogenation, producing methyl plus hydrogen, a second barrier to produce methylene plus 2 hydrogen atoms from the methyl group. Then there is a small barrier to produce CH plus 3 hydrogen atoms, and then a big barrier to fully decompose the molecule. But what is important here, for the case of the flat surface, is that CH3 is quite stable, kinetically stable. You can see that to decompose CH3 into CH2, there is a barrier to overcome that is almost 1 eV, 0.83 electron volts. That is similar to the barrier for CH3 to recombine with hydrogen and come back to vacuum. So this is quite stable. In contrast, CH2 is not stable at all, because with a very small energy barrier, it is a very small energy barrier that must be overcome for CH2 to become CH plus H. And this is the landscape we obtain in DFT calculations, and it is in agreement with experiments, in the sense that they observe a species that is associated to CH3. Then when they heat up the surface above 270 K, they observe a species that is CH. So CH2 is not observed at all in experiments, in a flat surface. And this is quite well accepted, and there is no doubt about that in the case of the flat surface. So in experiments with the stepped surface, these results, the RAIRS results for the flat surface, are taken as a reference, okay? We have to keep that in mind. So let's see what happens if we do the same for platinum 211. And the most striking and interesting result is that the relative stability of CH3 and CH2 completely change if we look at the different species that are produced by dehydrogenation of CH4 in the step. And what we observe, in fact, is that CH2 in the step of this surface is more stable than CH3 in the step. And in fact, the activation energy barrier that CH3 must overcome to become CH2, to decompose, to lose a second hydrogen and become CH2, is very small, 0.23 electron volts and 0.12 electron volts if we also consider 0-point energy effects. So the first take-home message from our DFT calculations is that in the case of the stepped surfaces, if we look at the methyl group in the step, the relative stability of CH3 and CH2 that we had in the extended flat surface has completely changed. It has been completely reversed. CH2 is stable, much more stable than CH3, that is almost not stable at all. The barrier here is very small. If we do the same, so if we estimate roughly the lifetime of a methyl group in such a state, taking into account that there is a small activation energy barrier of this size, and if we evaluate the lifetime like the exponential of the activation energy barrier, considering 0-point energies effect, divided by the Boltzmann constant and the temperature, and using a prefactor, a typical prefactor of 10 to 13 seconds to -1, we obtain that approximately the lifetime of methyl group in a step is 10 to -8 seconds. That is very, very small. And however, if we do the same for CH2, we obtain that is much more stable because the barrier to decompose CH2 is 0.48. What we obtain is an estimated lifetime that is 5 times 10 to 6 seconds. Our conclusion from these results is that in an experiment performed on this surface, platinum-211, at 120 K, the species that should be observed with a higher probability, if we are thinking about CH3 and CH2, is CH2, not CH3, because the lifetime is extremely small. Look at the difference, 14 order of magnitude in the expected lifetime. If we do the same calculations for the 110 surface with the missing row reconstruction, we obtain something similar, that qualitatively similar, that is the fact that CH2 is more stable than CH3 in the atoms, on the atoms that are called rich atoms that look like the step ones on the 211 surface. The barriers are smaller. The barrier to dissociate CH2 is slightly smaller than in this case. That means that CH2 would be less stable than here, but still CH2 is more stable than CH3, and the activation energy barrier that must be overcome to dissociate CH3 into CH2 is still quite small. At 120 K, the estimated lifetime of CH3 is very small. So what we did is to perform a frequency calculations for CH2, that is the stable species we obtain in our calculations. Of course, this plot corresponds to the methyl group in the step side. If we do the same in the step, the energy profile looks very similar to the one in the extended 111 surface. That means that for methyl groups in the facets, in the terraces, the stability is similar to the 111 surface. That means that CH3 is more stable than CH2. So what we propose is that when they perform the experiments, what they have in the steps is a species that is not a methyl group, but the methylene group, CH2. And what they observe in the terrace sites is CH3, like in a big flat 111 surface. So we perform the frequency calculations for CH2 in the step, CH3 in the terrace, and Eureka, we obtain a frequency that the species in the step, that is CH2, slightly larger than the frequency of CH3 in the terrace, in agreement with experiments. So good news, we have now a first possible explanation. So what we did is to perform the calculations for CD4, because when we don't know very well how to assign peaks in spectroscopy, isotopic effects is a powerful tool. So we did the calculations for CD4 and for CD2, for the product of CD4 dissociation, CD2 in the step and CD3 in the terrace. And we obtain again that the frequency of the peak of the species in the step is higher in frequency than the one in the terrace. And interestingly, the shift increases when we look at the deuterated species. However, that is in agreement with experiments. The shift they observe when they dose the surface with CD4, the shift between the peak corresponding to the species in the step is higher than the frequency of the species in the terrace by 35 centimeters minus 1. That is a factor of 2 higher than what is obtained for for the hydrogenated species, not without deuterium. So we also can explain this isotopic effect. By the way, this isotopic effect is unexpected if the species in both sides are the same, because we would expect a similar ratio of about a decrease by a factor of 1 over square root of 2. And if you have two peaks that different frequencies, if you divide both frequencies by the same factor, that is square root 2 coming from the different mass between hydrogen and deuterium, if you take two numbers and you divide the two numbers by square root 2, the difference between the divided numbers is smaller than the difference between the original ones by a factor of square root 2. However, the experiments show a factor of 2 bigger in the difference. So this point to this experiment cannot be explained again with if the species is the same, and we can reproduce this behavior. So the last point, the second question was, okay, but what's the origin of the 5 peaks? Why does the peak of the deuterated species in the step split into peaks in the case of platinum 211? So we did the calculations and we obtained 5 peaks for when we simulate what happened in this situation. But how did we obtain 5 peaks? Well, let's see. When we dose the surface with CH3D, we can, as I have already mentioned, that we can produce CH2D and CH3 in the terrace. CH2, sorry, here it should be CH3. CH2 in the, here there is a 2, no, let me see, sorry. No, sorry. All the possibilities are the following. When we consider that the species that are in the step have lost 2 hydrogens, two bonds have been broken, and for the species in the terrace, only 1 bond has been broken. So, if we consider this possibility, we have, in fact, 4 different species: CH2D in the terrace, CH3 in the terrace, CH2 in the step, in a bridge between 2 step sites, and CHD in a bridge site between 2 step sites. But what we have to take into account is that when we have CH2 in the step, it is in the carbon atom is in a bridge site, and the 2 bonds are perpendicular to the step, like in this picture. And this group cannot rotate freely with respect to this axis. Why? Because here, here you don't see, but there are 2 bonds between the carbon atom and the platinum atoms, okay? Because a carbon atom is in a bridge is forming a bridge between 2 platinum atoms, okay? So this carbon atom has a sp3 hybridization. So if you have 2 legs of of the carbon atom, the 2 orbitals like this and the other like this, rotating and becoming the 4 orbitals forming a plane cost a lot of energy. For CH2, that is forming 2 bonds with 2 platinum atoms, CH2 is not able to rotate freely around the normal to the surface. That means that when the molecule dissociates, if it is produced a CHD group with deuterium pointing to the step and hydrogen atom pointing to the terrace, the molecule cannot rotate and exchange. Of course, there will be another molecules that produce the product in the opposite direction, with hydrogen pointing to the step and the deuterium pointing to the terrace. But since these groups cannot rotate, we must consider these two groups as separated, as different species, CHD and CDH, depending on if hydrogen points to the terrace or if hydrogen points to the steppe. So these species that are in principle the same, CHD, might produce, and in fact do produce, different frequencies when we do the calculations. And this is the origin of this shift between the frequencies we obtain when we compute with DFT, the frequency of this species and the frequency of this species. So the partially deuterated species in the steppe, as mentioned by the experimentalists, produce two peaks because of this asymmetry of the surface. Interestingly, if we do the same in the case of platinum 110 with the missing row reconstruction, we cannot observe this splitting because it's symmetric. The shape of the surface is symmetric. So there is no difference between this species and this species. So in our calculations, the result is the same. And when they performed the measurements for this surface, they didn't obtain the splitting again of the species of the deuterated species that is in the rich atom. So again, everything is matching. I mean, the results we obtained from DFT calculations now explain most of the experimental findings, and in particular, all the open questions that were raised apparently are answered. So let me conclude and give you the take-home message is that the stable products of methane dissociation on steppe platinum surface at low temperatures, below 200 K, because if we increase the temperature, they are not stable, and they CH2 and CH3 lose extra hydrogen and become CH, and then only carbon on the surface. But we stay at these temperatures, they are stable, the species on the steppe here, the yellow atoms, and on the terrace, but the species that are produced are not the same. Methylene is the species on steppe atoms of platinum, and on the terrace, what is stabilized are methyl groups. So our DFT calculations our study now conciliates theory at the level of DFT with RAIRS experiments, and more interestingly shows our study that steppes not only tend to exhibit a higher reactivity than terraces, that is something that it is usually assumed and expected, it is not surprising at all, but it is a bit more surprising or interesting is that according to our results, also our results illustrate how steps can provide a route to produce surface selectivity controlled on the site. I mean, we can stabilize a product in the steppe, and we can stabilize another product of the reaction on the terrace. That might have interesting consequences if we are planning to produce a reaction of this intermediate state with another species, and that might reflect in a selectivity, in a different selectivity for a further reaction if something else that is absorbed on the surface react with a species that is in the steppe, that is CH2, or with a species that is in the terrace, that is CH3. So that's more or less all. Let me mention the people that is involved in this work. We did the calculations with a colleague from another institute of Rosario, Maria Eugenia Torio, and the experiments were performed, as I already mentioned, in Lausanne in the group of Rainer Beck. Also, we have discussed a lot we have drunk some beer also with Dan Auerbach. And so let me thank CONICET, the National Agency for Research in Argentina, and also this agency of Switzerland, because we had a bilateral project that provided funding to do this work that was done in collaboration with the experimental group. And let me so thank you for your attention.
Okay, so
Thanks for your attention. It's here, but I'm sorry.
So thank you for this interesting talk and for showing us that the DFT sometimes is also right, not like experimentalists want to say it always. That
no, even us, we say, okay, probably,
yeah, but
because the frequencies are very close to each other. And we know that computing frequencies is tricky. But we were optimistic at the beginning because for CO, for instance, the shift is reproduced qualitatively well. The frequency of CO on the same surface. On the step, the frequency we reproduce, the smaller frequency, and the shift between the frequency of CO in the step and in the terrace was reproduced well. So we say, okay, if it's more for CO, let's try, why not with for CH3?
Okay, is there any question in the audience? August?
During the study, did you use van der Waals functional? Yes.
Yeah, we did.
And so you expect van der Waals interaction to affect the variation or not much?
The frequencies might be a bit slightly different because when you introduce van der Waals, the geometry of absorption on each side change a little bit, and then the frequency might change, but the change affect both states in the state of the species in the steppe and in the terrace in the same way. That at least that was what we obtained, and it doesn't change the order. I mean, the species that without including van der Waals has the lower frequency still has a lower frequency when we do calculations including van der Waals. So does not change the scenario, even if the frequencies might change a little bit, but the ordering is preserved.
Okay, thank you.
Any other? No? Okay.
Okay, so thank you very much, Fabio, for this very nice talk. I was completely convinced that you have CH2 in the step by the calculations. So yes, one thing. At the beginning you said that it is clear that, but you see that in the experiments also, that that is more reactive in the step because you see the peak that is higher also than the other one. Mm-hmm. But there was some results here that you saw when you do it with the deuterated species. It seems to me that in the experiment they have a lower peak in the step. It is right. I mean, one of the strategies.
Yeah,
and this is why. You know what I mean, no?
I think
it was in previous.
Yeah. I know what you are talking about.
No?
Here.
Yeah.
Yeah. In principle, what they observe is that when they increase, this is for a very high dose.
Okay.
For a very high dose, they observe that the peak in the terrace become higher, more intense than the one in the steppe. And they say that this is showing that for some reason the mode they are exciting here is more infrared active than the one that is in the steppe. Since the geometry of absorption on the steppe and on the terrace is different, even if the species were the same, they think that this is the experimentalists say that it is due to the fact that the species here is more active to the for the excitation produced by the laser. If this is connected with the fact that they are different species, I don't know. But it is true that they are in a different environment because in this case, in the case of the species, even if we could consider that it is CH3 in both cases, in this case the molecule is perpendicular to the facet, and in this case is not perpendicular to the facet. The alignment of the dipole that is necessary to excite to produce the absorption is different. So it is unclear what could be the origin.
Yeah.
But it could be also due to the fact that they are two different species.
Probably this also applies to, I mean, so thinking about the 5 peaks there, no? I mean, you see that, I mean, the splitting between the 4th and the 5th, which are very similar species. One is but you see that the intensity is much lower for one of them.
Yeah.
So probably it's also some kind of this explanation will apply, no?
Yeah, but also in this experiment, we have to take into account that this is very close to this peak.
Mm-hmm.
And so the intensity we have here is also affected by the fact that it's a peak that is on top of the tail of the other peak. So yeah, but it is true that it seems that this peak is more intense than the other. I have no explanation for that.
Neither the experimentalists have. So.
No. As far as I know, they don't.
Yeah.
In fact, I'm showing one spectrum where all the peaks are very well resolved. Depending on the dose, depending on many things, sometimes that change a little bit. So.
Okay. Any other question, Alberto?
All these experiments are done always with the same direction of the beam respect to the surface. Is there any study like this?
You mean the laser or you mean the molecular beam?
The molecular beam. Like
in these experiments, they have been working, as far as I know, at the fixed and always the same geometry concerning the angle of incidence. However, they perform in the Reiner-Beck group, they perform measurements of the sticking probability of methane on this surface with the angle of incidence, and they have studied incidence in this direction, normal incidence, and also in this direction. I mean, almost normal to the facet and almost normal to the step, and they obtained some differences. Yeah, but this was reported in a different paper. They report the dependence of the sticking probability with this angle of incidence, and they compare with ab initio molecular calculations that were performed in the group of Hirti and Cruz. In principle, if I remember, if I don't make a mistake, the result, the IMD results agree well with the experiments concerning the dependence. But I don't remember, the dependence is not very, I mean, the sticking probability they observe in this direction and in this direction is not that different. But there is some difference. It's little, it's a small difference.
Any other question? I have one. I'm a bit disappointed because you haven't shown any dynamic calculation. So are you planning to do dynamics and see whether it's true that you find this CH2? Or...
Yeah, it's, we would like to do some dynamics to study the, well, it would be great to be able to simulate the dissociation of methane on this surface and be able to follow the dissociation product that at the beginning will be CH3, of course, but it would be great if we could do something to continue the dynamic simulation until finding the decomposition of CH3 into CH2. The problem is that the time scale might be very long, even if the lifetime of CH3 is very short for experiments, but might be extremely long for simulations. But it would be nice to do that.
But so you don't expect that you can have a CH2 on just at the very beginning?
Probably yes, because of the exothermicity of the exothermicity of the first dissociation, that the lifetime we estimated, were assuming that the CH3 intermediate thermalize, but probably a hot CH3 product can evolve into CH2 even much faster, and it would be nice to be able to see that. In that direction, we have started with the very simplest case, and we have set up already in our group a potential energy surface to describe hydrogen interacting with this surface, because to follow this process, hydrogen will stay on the surface after dissociation. So we started our project in this direction, generating a potential energy surface for hydrogen on platinum 211, and we did it with a neural network, and we already have results for molecular dynamic simulation, and to study the temperature dependence of the diffusion coefficient of hydrogen. And so this is the first step. The next step would be to see if we can add CH3 co-adsorb with hydrogen and generate a potential energy surface able to be used then in molecular dynamic simulations. And if we can, and if we succeed, we could do something. And also, if we can also, with the same potential energy surface, describe the dissociation of CH4, we might put all the pieces of this puzzle together and describe all the process. But it is work for several years, I think. But we are in this direction. We can describe with neural networks CH4 dissociation on platinum 110 with reconstruction. It is almost done. We have then the diffusion of hydrogen. We have to put now CH3 with hydrogen, or both together on the surface, and see if we can succeed to reproduce, to have a good representation of the surface.
Okay.
But it's a challenge.
Yeah. So, any other question?
I have a last question.
Which
is the time scale, or which is the time limit in your DFT calculations? Just for how long are these simulations lasting?
What kind of simulation are you talking about? Because the results I've shown here are consisting, well, we determine stable species by performing the geometry optimizations as usual. So that's not too long. The difficult part was, or the much demanding time, demanding part was the obtaining all the transition states for the different decomposition processes, and this takes much more time, because we have to do not just elastic band calculations and different test calculations, etc. So this is the most time-consuming part. How long they are? Each individual calculation is very fast, because the unit cell is not big, so we can do several calculations in 1 hour using several processors. But the problem is that we have to. I've shown the result, a summary of the results of several months of calculations, because we perform many calculations for different sites, different species, transition states, and then the frequencies. The frequencies is not the problem. We simply diagonalize the Hessian matrix. It is an harmonic approximation. That's not too expensive.
Okay.
And including the surface degrees of freedom doesn't change the frequencies of the molecule. So it is always the frequencies I've shown here correspond to a frozen phonon approximation. Only the modes of the molecule have been computed in this case. We did it including the motion of surface atoms, but it didn't change the frequency of the symmetric stretching mode.
Thank you.
Oh, we should stop here, okay? So Fabio is there in the CFM, and any other question you can just ask to him. Okay, so thank you very much, Fabio.